In this video, I'll be talking about electric field due to parallel conducting plates. Let us consider we have two infinitely long parallel plates. The one is positively charged and the other is negatively charged. And we are interested in finding out the total electric field outside, between the plates, and again outside the plates. We assume the sigma is the surface charge density of each plate. The sigma is the surface charge density of charge plate. What does the surface charge density mean? The surface charge density means charge per unit area. How much charge you have in unit area is called the surface charge density. And in the last video, I already have talked about what is the electric field due to one charge plate. If you have only one charge plate, what is the electric field? Is here. So if you have only one charge plate, which is an infinitely long charge plate, then the electric field value, this is the electric field value. That's the electric field value due to one charge plate. And the direction of the electric field is always outwards if you have a positive plate. And what you have to notice here, this electric field is independent of the distance. Okay, it does not change with the distance. And the electric field is always perpendicular from this surface. Okay, with this information in mind, let's now calculate what is the total electric field outside. Okay, so we just going to we have a point here outside. First, forget about this negative charge. Due to this positive charge, the electric field will be away from the point. Okay, this is the E positive, and due to this negative charge, the electric field will be towards the plate. So the electric field due to the negative charge is towards the negative plate. And as we notice, these two electric fields does not depend on the distance. They are exactly equal in magnitude and opposite in direction. The electric field value due to H is sigma over 2 epsilon naught. Okay, this value is also sigma over 2 epsilon naught, both due to the plates. This is positive and this is negative. So what is the total electric field at this point? It is exactly 0. So the total electric field outside the region is 0. Now let's talk about this region now at this point. Again, at this point, at somewhere, the electric field due to this negative plate will be towards the plate. That means this is the E negative. And due to this positive plate, it will be away from the plate. So this is away from the plate. Again, what you notice here, both electric fields are exactly equal in magnitude but opposite in direction. So the total electric field at this point is again 0. So outside the plate, there is no electric field. The electric field exists only between the two plates, this way. Okay, now let's find out what is the magnitude of the electric field. So let's say we have a point here, and at this point, due to this plate, the electric field will be away from the plate. So this will be E positive. Okay, and due to this negative charge, the electric field at this point will again be towards the plate. So this is E negative. And both electric field inside the region, inside the plates or between the plates, is exactly in the same direction, and the magnitude are again equal. So the total electric field will be the addition of two, E plus E minus, and due to one plate it is sigma over 2 epsilon naught, and due to another plate it is again sigma over 2 epsilon naught. So what you get the total electric field? The total electric field between the two plates is given by sigma over epsilon naught. So this is the electric field due to in between the two charge plate. Okay. And now we're going to talk the same thing, but rather in a different way by using Gauss law. Okay. So let me erase something, or I'll make another video for this one where I will be talking about electric field due to a parallel conducting